Welcome back to the module 14. We are discussing Maxwell's equations in the medium. What we have assumed here, the medium should not have any free charge in the medium, and that's why rho, which is volume charge density, becomes 0. If it is 0 in the medium, then I can write down this expression. This is nothing but the expression for D, that is the electric flux density, which includes the vacuum contribution and the nonlinear polarization contribution. This is simplified to this equation, and finally I can write this equation. Now question is, in the equation which we have already got, this is the equation we have got after getting triple product. We remind ourselves that this is the equation we have got, minus E equals mu naught d dt. Okay. Now in order to, in vacuum we have seen that we have made it 0. Question is, in the medium, can we do that? In the medium, it is not necessary that divergence of electric field would be 0. It is not always necessary, but if we consider very weak nonlinear polarization, this is a perturbative limit. We are considering that I have a medium, input beam is propagating through the medium, that is creating this nonlinear polarization. This nonlinear polarization is very weak, and however this weak nonlinear polarization can create another field which is called emitted field. So if we consider that very weak nonlinear polarization, then we can assume that this PNL is very small, and if it is very small, then we can consider to be negligible or 0. So under this weak field approximation, weak nonlinear polarization approximation, I can make this field to divergence of the field to be 0. In that case, this becomes 0. So this component becomes 0, and I get this expression. This expression can be rewritten as this. This is called perturbative limit of nonlinear effect, and under this perturbative limit we get the expression which we used previously as fundamental equation of nonlinear optics. We can reduce it to one dimension and we get this expression. This expression was used. We remind this expression here, E is not emitted, E is not input beam, E representing emitted beam. There are 3-step model: input beam field is expressed by E input. Due to propagation of the fundamental beam through the medium, I am creating this nonlinear polarization. How they are related? They are related by this Taylor series expansion. Then this nonlinear polarization is nothing but oscillatory dipole. Any oscillatory dipole would be a source of electromagnetic radiation. So I am creating this new field, and how this new field and polarization are related, this is the expression which relates this nonlinear polarization and the new field. To obtain a simplified picture, we have considered this propagation along the z direction, that's why it's z dependent, and EZT represents emitted field. This EZT is the emitted field. Or fundamental beam. PNL features a nonlinear contribution to the polarization, suggesting that nonlinear polarization acts as a source for emitted field. This equation enables us to calculate nonlinear effects, the second and the third order, due to propagation of ultrafast pulse in dielectric medium, non-magnetic medium, source-free medium. So this equation is valid for dielectric medium non-magnetic medium, a source free medium, and we have also assumed that we have weak nonlinear effect, that is under the perturbative limit. We have seen this equation previously, but we haven't done the derivation before. Now, to obtain the solution, we used slowly varying envelope approximation. We have seen this approximation before, and we assumed the form of emitted field as a pulse with a center frequency omega naught and wave vector k naught, and nonlinear polarization also having an envelope function similar to pulse and its frequency components omega naught. So, what is the idea? Idea is that oscillatory dipole is nothing but representing this nonlinear polarization, and the frequency of those dipoles would be equivalent to the or the same as the frequency of the emitted field. That is why frequencies are the same for polarization and emitted beam. But it may so happen that their phase, that is k naught and kp, they can be different, and this is very common. If we have k naught equals kp, then we call it the process is phase matched, and if they are not equal, we call it process is not phase matched. So, here in this to obtain the solution, in the trial solution we have considered the same center frequency, but different wave vectors k naught and kp for the emitted beam and the nonlinear polarization. In addition, here we have considered complex notation of the electric field and the nonlinear polarization, as the complex notation makes the mathematics simple. However, we shall remember that in the end of the calculation we need to take the real part Ez. So, now question is how they are related. This is something which we need to find out. In the end, I need a solution for Em, because electric field, if I know emitted electric field, then I know emitted field intensity, and I want to find out what are the factors which can control the field intensity of the emitted beam. That is exactly what we want to know, because this field intensity of the emitted beam is nothing but the conversion efficiency of 800 nanometer frequency component. So, if I want to find out what is the efficiency of the conversion, frequency conversion, that will depend on this intensity. So, I need to know this field strength from this equation. Furthermore, here we have considered that due to propagation of input fundamental beam with omega 1 frequency. So, omega 1 frequency is the fundamental frequency, and polarization is induced in the dielectric non-magnetic source free medium. The frequency of the induced polarization is omega naught. So, here this is emitted beam, and if I need to write down input beam ZT, then I have to write down let us say another field, that is E field, let us say that is E naught field, and then e to the power I omega 1 t minus k 1 z. This is your input beam. So, there are 3 steps. Input beam is creating nonlinear polarization, nonlinear polarization is creating the input beam emitted beam. If the second harmonic generation is considered, then we can write down omega naught equals 2 omega 1, which means oscillating dipole is the source of electromagnetic radiation, and that is why the new light is created at the same frequency of the induced polarization. However, the phase of the induced polarization and the emitted field may be different. That is why it is shown here. This fundamental frequency omega 1, this omega 1 is propagating through the medium, this beam is propagating through the medium, taking an example of plane wave. At each point of the medium, we are creating nonlinear polarization, which is oscillatory dipole, and each dipole will produce some field, that is the emitted field, at a omega naught frequency, which is nothing but 2 into omega 1 if I consider second harmonic generation. These fields are in phase. So, if we can create all these fields in phase, then we call it phase is matched and we get maximum intensity from SHG process. But if the fields are not matched, if the fields are destroying each other due to destructive interference, then in the end we will not get any conversion for SHG. That is why it is very important to understand how the K naught and Kp they are related, because these two quantities are going to contribute to the conversion efficiency. When an ultrafast pulse propagates in a dielectric medium, in addition to nonlinear effects, the pulse experiences dispersion. As ultrafast pulse has broad bandwidth, different color or frequency components experience different refractive indices while propagating, resulting in dispersion effects, which cannot be realized within the time domain representation of the pulse. For that, we need to represent the pulse in frequency domain. In order to incorporate dispersion effect as well, we shall represent AZT in terms of its Fourier transform. So, the basic idea is that I cannot use when a pulse is propagating through the medium, I cannot use its time domain representation. I have to use frequency domain representation, because frequency domain representation can incorporate the dispersion effect and the pulse will experience dispersion effect. Now, this pulse is the emitted beam. That is why AZT is expressed in terms of frequency, and this is nothing but the Fourier transform, inverse Fourier transform. And if we express this in the field, then I can write the field as inverse Fourier transform of the envelope multiplied by carrier wave in the time domain. So, this part in the frequency domain, and this omega bar is nothing but a conversion of the variable. E omega, it is centered at, so this is A omega, this A omega is centered at omega naught, that we know. So, if we make it centered at omega 0, then I can define this omega bar, a new variable, which is nothing but omega minus omega naught. This is a new variable. So, this field, now I have expressed this field as, it depends on Z, it depends on T, and it depends on omega bar as well. Now I have incorporated time frequency dual domain expression. This is a dual domain expression. I need this dual domain expression because dispersion effect can only be realized in the frequency domain. I should have this frequency domain expression. So, what I get in the end we can simplify this expression. We can multiply this e to the power I omega naught t and e to the power I omega bar t, and finally we get this expression where polarization expression is familiar to us. This is the trial solution we have taken already, but emitted field is expressed in terms of z, t and also omega, and we will consider that this field is propagating through the medium. So, all we need to do is that we have to plug that in this expression finally, and we have to get this second derivative with respect to z, second derivative with respect to t and second derivative with respect to t of the polarization. So, these are the terms we need to calculate to plug that in. So, we will take the first derivative of the electric field. If we take the first derivative of the electric field with respect to z, z dependent term is A, is z dependent, and also this is z dependent. So, I get this expression, the simple derivative. Second derivative I take and I get this expression. Now, we will employ slowly varying envelope approximation. Slowly varying envelope approximation, it suggests that the envelope function varying slowly in time, and varying slowly, it means that I can consider the second derivative to be 0. It is varying so slowly that the variation, the gradient of the gradient is 0, or approximately can be considered to be 0. So, this slow variation leads us to a reduced expression for this equation, where second derivative is taken to be 0. Now, we will take the time derivative. We consider time derivative, and remember A z omega is not time dependent. Time dependent part is the just this carrier wave. That is why this part can be very easily rewritten like this way. And another time derivative we have to take polarization expression, we get this. Finally, polarization expression can be written like this way, second derivative. And here we have to consider one thing. We will consider that under SVEA, second derivative of this term is 0. This is SVEA approximation, second derivative is 0. In addition to the second derivative, I will consider the first derivative to be also 0, because we considered weak nonlinear polarization. So, polarization, nonlinear polarization is so weak that its first derivative is almost 0. So, approximately I can write down the nonlinear polarization expression as like this. Thus, one can insert all the expressions into the one dimensional equation of nonlinear optics, and we get this expression. We can rewrite this expression as this, and again we can rewrite this expression like this. These steps can be easily obtained. Now, at this point we will insert the dispersion relationship. This kind of dispersion relationship we have seen in dispersion effects of nonlinear pulse propagation. So, this mu naught epsilon omega naught, mu naught epsilon omega square, this part can be written as k square, and k depends on omega. If we write a general expression for k, then we get this k omega. This is a general expression for k. This is k square. This means k square. So I can write down this square to be like this, because k omega plus k naught, this is approximated as 2 k naught. That's why you can write down approximately like this. So I get this expression, and rewriting this expression one more time here, and we get this expression like this. Now this k omega, we do not know the general form. That's why we are going to express it in terms of Taylor series expansion. All we know that the k at omega naught value, I know the value of k, that is k naught, and I know the derivatives exist. So that's why we can use this Taylor series expansion to express k, and different parts of this expression representing different kind of dispersion that we have seen already in the dispersion effect in nonlinear pulse propagation. For an example, the second term, this term is the vacuum term. If we do not have any other term, if we have this term, then this is a vacuum term, no dispersion effect. Then the first order term I can introduce, first order term representing the group velocity. So the effect of group velocity can be judged only if we include this first order term. Then there is a group velocity dispersion term, GVD, which can be realized with the help of second order term, second order dispersion term. So what we will do here, we will consider this problem for the first order, up to the first order. We will neglect every other terms. Then we can write down that approximately this k omega can be written as like this. We know that omega bar is nothing but omega minus omega naught, that is written here, and Vg, group velocity, we have seen previously, it is d omega dk at omega naught. So this is 1 by Vg. If we insert that, then I get this expression, rewriting this expression little bit here, and finally we, after rewriting these expressions, we get this, and we have again changed the variable, because remember d omega, we have expressed omega equals omega minus omega naught. So d omega, sorry, omega bar equals omega minus omega naught. So d omega bar is nothing but d omega, and that's exactly what we have written here. So the derivative we have changed with respect to d omega bar, here also d omega bar, and this was the definition of AZT we have seen in terms of frequency. This is also frequency dependent, and if we take the first derivative with respect to z, I get this expression, and with respect to t, I get this expression. So what does it mean? It means that this first term is nothing but the derivative of A is the field envelope of the emitted beam with respect to Z, and the second term is representing the derivative of the field envelope of the emitted beam with respect to T. Finally, we can write down this expression. Here what we have done is that this was the expression we have got from Maxwell's equations. And using these trial solutions, we have found a solution. Solution was like this. Plus 1 by Vg del T equals minus I omega naught square mu naught omega naught square divided by 2 k naught bzt e to the power I k naught minus kp z. So, this was the expression we have got finally. Then what we will do is that we will turn off this time dependent part and we will just look at the space dependent component. This simplification or transformation is like turning off the time dependence to monitor space dependent effects only, and this can be practically realized if we transform the time coordinate to be centered on the pulse. If we do that transformation, then we can turn off this time dependent component and we have this space dependent component only. This simplification will ultimately lead us to the understanding of an important concept which is called phase matching in nonlinear medium. When a nonlinear process holds, that is k naught equals kp, then I have this expression delta k is nothing but k naught minus kp, and this delta k, if it is 0, then the process is called phase matched. So, if I have k naught minus kp, k naught equals kp, then delta k becomes 0 and we call it a phase matched. But if we do not have phase matching condition fulfilled, then we have to integrate this expression to get the intensity, final intensity, because we are interested in final intensity, how much intensity I can get. We see that the final intensity depends on L square, that is the medium length. Definitely if we use thicker length, if we use thicker crystal, we will get higher yield, but we also have to remember that it depends on this also, which having L contribution. This is called cardinal sine function. So, it depends on the behavior of a cardinal sine function. I have an input beam now, I have an emitted beam due to nonlinear polarization. Now, this emitted beam intensity I depends on this cardinal sine function. If it is phase matched, then always the intensity will grow, but if it is not phase matched, then intensity will drop down very quickly as a function of the length. If we increase the length, it will drop down immediately. We have seen all this behavior in module 3 already. So, to achieve phase matching for high harmonic generation, it is necessary to find out a nonlinear medium for which refractive indices at omega 1 and 2 omega 1 are the same. Unfortunately, the index of refraction varies with frequency of radiation. This is a phenomena called dispersion effect. Therefore, phase matching condition cannot be fulfilled in any medium. The solution is to use birefringent crystal. This is also we have seen before. In the birefringent crystal, we have ordinary and extraordinary beams, and one beam polarization can be in phase with the emitted beam by the other field, and that is the basic idea how we achieve phase matching in birefringent crystal. In birefringent crystal, when light propagates, it is decomposed into two beams with mutually orthogonal polarizations. These beams are called ordinary beam and extraordinary beam. Refractive indices are different for ordinary and extraordinary beams, and therefore, it is possible to achieve phase matching for center frequency component, that is shown here by omega 1 and 2 omega 1. this is an analysis of phase matching condition taking one frequency component only. So, one can say that okay, for omega 1, this is omega 1, this refractive index can be same at omega 2 omega 1 and they can be the same. This is possible and we can say that phase matching condition can be fulfilled. But we have to remember that even at the center frequency component, if we have phase matching, let us say this is these 2 points, they are having phase matching because their refractive indexes are the same. But if I have a with other frequency components, for an example this frequency component having refractive index here and corresponding, this is I call it omega 2, then this is 2 omega 2, at 2 omega 2 I have refractive index different, which means that at the center frequency component I can have phase matching, but other frequency components I may not have phase matching. And we have to remember that a pulse will exist only when all frequency components should be present or many frequency components should be present. So, what might happen in a nonlinear medium, for a particular frequency component I can achieve phase matching, and that is why I can have emitted beam intensity for that frequency component 2 omega 1. But other frequency component, because they are destroyed, because phase matching is not achieved, in the end I do not have a pulse, because in order to exist, in order to obtain a pulse at 2 omega 1 frequency component, center frequency component, I need all the frequency component to be present. So, this is 2 omega 1, there are many other frequency components should be there here. That is why phase matching bandwidth is very important. We shall for simplicity consider SHG process here with an ultrafast pulse. The range of frequency components or wavelength components that achieve phase matching is called phase matching bandwidth. So, question is, if I have, this is your omega 1 input beam, this will be converted to 2 omega 1, 2 omega, this is omega. So, this is nothing but nonlinear frequency conversion in frequency domain. I am creating 800 pulse, from 800 pulse I am creating 400 pulse, 400 nanometer pulse. Now, in this conversion process we have to remember that very easily I can get a phase matching condition fulfilled for this frequency component, but it is not necessary that I will be able to achieve phase matching condition for other frequency components as well. And if I cannot achieve phase matching condition for other frequency component, the pulse will break down and I will not have any pulse anymore at the higher frequency. So, phase matching bandwidth is very important. Question is, how many such frequencies can be phase matched? Delta omega, that is called phase matching bandwidth. So, what we are going to express is that we are interested in delta k. So, delta k can be expressed as this. This is an expression which we have seen previously. This is nothing but k naught and this is nothing but kp. Here second harmonic generation we have considered. So, kp is expressed like this way and k naught is expressed like this way. In terms of wavelength, we can immediately express like this way. So, this 2 does not exist here. No, they should exist here. They should be there here. Okay. So, finally, what we see is that delta k in terms of lambda we can express like this way, and we will assume that this lambda 1 is nothing but lambda naught plus delta lambda. So, if we express like this way, then 4 by lambda 1 is 4 pi by lambda 1 can be expressed as this, which is nothing but this, and then finally express this, and one can write down this because it is just because lambda naught is much greater than delta lambda. So finally what we get is an expression like this, and what we are expressing here is refractive index in terms of Taylor series expansion at centering this wavelength and this wavelength. So we plug that in, finally we get this expression, and because it is phase matched at lambda naught, we can write down that n lambda naught equals n lambda naught by 2. This is what we can write down, and that's why you can reduce this expression, and finally we get an expression like this, where we are neglecting square terms, delta lambda square terms. So this term has been neglected because we have a square term. So this is considered to be 0. So finally what we get is this expression, and further we can reduce the expression in terms of delta lambda. What we get, delta lambda equals this delta k by this, and from intensity we know that the intensity will depend on the cardinal sign function. So from that expression we know that the function, this kind of cardinal sign function, will decrease to half of its maximum intensity when I have this value delta k L by 2 equals 1.39. So I will consider that the intensity will go down to 0 when I have twice this value. So which means I am not here at this point, I am actually here in this point. So I can write down this expression, and finally delta k has a relationship with the thickness. So if we plug that in here, we get delta lambda inversely proportional to L, delta lambda inversely proportional to L. What is important here to note here is that if we have a nonlinear medium and if we have a very short pulse will have a large delta lambda, thin crystal we need. So this is suggesting that although in a medium I may achieve phase matching for the center frequency component, but in order to gather other frequency component I need to use a thin crystal. The shorter the pulse is, thinner the crystal we need. So this is the take home message we have. With this we have come to the end of this module. In this module we have gone over more details of the Maxwell's equations, its implementation in understanding plane wave propagation in the vacuum, then ultrafast pulse propagation in the medium, and how we can use Maxwell's equations to understand different phenomena in ultrafast optics. We will meet again for the next module.